question, we have a uniform mass rod of mass m and length is L. A force F1 is equal to 2F magnitude is applied at this end perpendicular to this, and at a distance x from C a force of magnitude F is applied in this direction perpendicular to this length. We are asked what is the linear acceleration of this rod, what is angular acceleration of this rod, and what is where this point P is located, which is going to have net acceleration is equal to 0 as seen by a person on the ground or with respect to ground. So first, as usual, we use the principles of linear mechanics, that is net force is equal to mass into acceleration. So F1 plus F2 is equal to mass into acceleration. So this 3F, 2F plus F, that makes 3F, 3F is equal to ma, so acceleration comes out to 3F by m. So this is the linear acceleration of this rod in this direction, that is acceleration of center of mass is going to be 3F by m. But this acceleration of center of mass will also affect the net acceleration of all the particles on this rod. Now let's talk about the torque. Because the torque, there is going to be some alpha. When there is going to be some alpha, then there is going to be some tangential acceleration, because A tangential is equal to R alpha, and the net acceleration of the net acceleration of any point on the rod is vector sum of these two accelerations, that is A tangential, that is R alpha, and the acceleration of center of mass, and these two when we vectorially add, we get the acceleration of that point. Now let's use torque is equal to I alpha, and we take the torques about this center of mass. So over here, this force is trying to rotate it this way, whereas this force is trying to rotate this way. If we do it like this, if we put a nail over here so that this can rotate like this, if we apply a force in this direction, this is trying to rotate it in the clockwise direction, whereas this force is trying to rotate in the anti-clockwise direction. Obviously, this magnitude is more, this distance is more, eventually this is going to have alpha in this direction. So torque is equal to I alpha when we use, so 2F into this is distance is L by 2, 2F into L by 2, that is the clockwise torque about this axis, and F into X is the anti-clockwise movements in this direction. So net torque is 2F into L by 2 minus F into X, that is net torque, is equal to I alpha, I about center of mass of this rod of mass m and length L. What is that? That is ml square by 12 into alpha. So this is going to be like this. So from here we get alpha as 12F brackets L minus X upon ml square, that is this 2 and this 2 goes off. So this is FL, this is Fx. So F can be taken out, F L minus X, 12 comes over here to here, and in the denominator ml square. So this is alpha comes out to be like this. Now we find, so this is alpha. So angular acceleration of this rod is, this is the angular acceleration. So we have both the things so far. That is, we have got the acceleration of this rod as 3F by m, and the alpha, that is angular acceleration, is this much. Now we come to the third point. That is where this point P is located, so that it is going to have, this point P is going to have zero acceleration with respect to ground. Now this is being affected by two acceleration. One is because of tangential acceleration because of alpha, that is AT is equal to R alpha, we shall be using it, and on that we'll superimpose vectorially this acceleration of center of mass, that is this one, and the net resultant of these two actions, that should be equal to 0. So over here, if we see acceleration of P with respect to 0, so that means that acceleration of P vectorially, once again this triangle of acceleration only, that is, we say this is acceleration of P and this is acceleration of C with respect to ground, and this is acceleration of P with respect to C. That is, acceleration of P is vector sum of AC plus A of P with respect to C, triangle of acceleration, and that should be equal to 0. Now what is acceleration of P with respect to C? That is going to be equal to R alpha, that is X into alpha, it will be in this direction, it is rotating in this direction, so A tangential will be in this direction, and A tangential will be equal to R into alpha, that is AT is equal to R alpha. This should be equal to what? That is, should be equal to, that is acceleration of center of mass, that is same acceleration shall be added vectorially on all the points on the rod. So over here this acceleration should be equal to, that is 3F by m, that is the acceleration which we have got earlier. So this AT is going to be equal to X alpha, that should be equal to this. So that's why then, if this is equal to this, then the net acceleration of point P as seen from the ground will become equal to 0. So X alpha is equal to 3F by m. We put the value of alpha over here. So this comes like this, 3f by m. So when we solve it, this eventually it becomes a quadratic equation in x. We put the values and x comes out to be L by 2. So at a distance x is equal to L by 2, this point is going to have zero acceleration with respect to ground. With respect to center of mass, it is going to have A tangential is equal to R alpha, that is x alpha. This will have acceleration with respect to this. It is only that is with respect to ground, this is going to have zero acceleration.